Hi
Hi everyone,
everyone,
I'm Sirui Wang.
I'm Sijia Wang. We're here for presenting our paper Mouillé, exploring wetness illusion on fingertips to enhance immersive experience in VR. Wetness perception is a kind of feeling that an object or environment contains moisture. Think about when you touch the running water, or you're in a rainy day, or you are sweating. This ability to sense skin wetness and humidity is critical for behavioral and autonomic adaptations, which help us for survival. We know that HCI haptic works in VR environment mostly focused on pressure, vibration, shear force, feedback, thermal sensation, and etc. But there are few works about wetness sensation. So we wanted to explore this underdiscovered topic. 100 years ago, a scientist called Bentley found that when he put his finger into a bottle filled with cold water and covered by a rubber sheet, he felt his finger was wet. And he hypothesized that the wetness perception is a combination of coldness and pressure. Enlightened by Bentley, other scientists started to explore humans' ability to sense wetness on the skin. They first did some dry-wet experiments by dripping water on different fabrics and then applying on skin. The result shows humans are quite sensitive to humidity. We can feel 1/10 drop of water on a multiple 5 centimeter cotton pad. Then, scientists explored how thermal and tactile stimuli can generate wetness illusion based on previous hypotheses on different body parts. They found thermal sensation might be the main factor. For better understanding of how we feel wet, Dr. Filingo and his team developed a neurophysiological model of cutaneous wetness sensitivity. Mechano A beta, cold A delta, and warm C sensitive nerve fibers, and their projections from the skin through peripheral nerve, spinal cord, thalamus, and somatosensory cerebral cortex are shown in this model. It proves that coldness is the main factor for invoking wetness perception. Even cold dry stimuli can bring people wetness feeling, and light touch can strengthen the wetness sensation. As you can see in warm moisture situation, people can only feel humidity when light touch applied. So what we want to do is to generate a handheld VR device. Because fingertips are rich in peripheral nerves, so that it is very sensitive to wetness, and finger interaction is important in VR environment. In terms of the wetness illusions, there is no systematic explorations combining thermal and tactile stimuli on fingertips. For understanding wetness illusion on fingertips, we modified a 3D printer by taking advantage of the 3-axis gantries. One end of the original printhead was replaced by a temperature electrical cooling plate, which is TEC plate. It is connected to a water cooling equipment. The temperature of the TEC plate was controlled by a TEC control unit. The other end the other end of the printhead was attached with an FSR sensor for measuring the pressure. Two pieces of holders were positioned on the original printing plate to dock users' fingers and hands. So when started the test, the platform moved the x-axis slice to drive users' fingers towards the TEC plane until touch it. By measuring the pressure via the FSR sensor and adjusting the printing plate position in the x-axis, we could precisely control the pressure that was applying to the fingertip. So, by manipulating the movement of TEC plates in the y-axis back and forth, we could create different levels of friction sensation. Inspired and informed by previous research, we use our test equipment to generate 3 different types of cold dry stimuli, including uh, 5 temperature, 15 pressure, and 10 friction tasks. The study was conducted in a quiet office with stable room temperature and relative humidity. Participants were asked to measure their fingertip temperature by a thermometer and then immerse their index finger into water, allowing them to get a baseline wetness feeling. They were separated from the device so that they didn't know anything happened in the device to prevent any expectations. For each trial, each participant positioned their index finger in the holder on the printing plate, which then automatically moved their fingers towards to the TC plate until the measured temperature, pressure, friction satisfied with the configurations of the trial. Then the participant was asked to rate their wetness, pressure, and friction sensation on their fingertip using the described scales. This phase took roughly like 20 seconds. After that, the TC plate was set to the original temperature of the participant's finger to warm the finger back to its original temperature. The phase stopped when the participant indicated that the temperature of their finger was the same as that the TC plate. Then the plate moved back to the original position with the finger. After analyzing the data from 12 participants, we got the results. As you can see in the figure, the lower temperature, the high wetness perception. And pressure has a positive effect on the wetness sensation when it presents. Also, ratings for all friction levels were very similar. So we know that the thermal sensation is the main factor for wetness illusion. There are something really interesting during this study. Since all the participants, they didn't know what happened in the device, they will have some imaginations. So as you can see, the first participant commented that I feel my finger was wrapped in a sponge full of water. And the second participant says that it was like I just put my finger out of water. And the other participant commented that I feel like touching a tin can in winter or ice pump in summer.
As a result, the prototype should be able to generate different levels of temperature change, and we should also consider to allow users to apply different levels of pressure or friction. Based on the findings of previous study, we designed Muli, a prototype that generates wetness illusion on users' fingertips when they touch, squeeze, lift or scratch its surface. Muli was designed to help enrich immersive experience with wetness sensations on users' fingertip in VR context. It comprises of 3 parts, including the stiffness control components for rigidness and elasticity, the components that leverage the TEC plate into the rapid cooling on a copper plate, and the components that serves as the contact surface with users' fingers. The capabilities of Muli are to render wetness illusion for rigid and flexible objects as well as table surfaces. For example, to stimulate a Coke bottle, the lock system is unlocked so that the 2 vertical side surfaces can be squeezed, and the bottle motor rotates 180 degrees and pulls the spring down, which is pulls the 2 side surfaces into the body of Muli, so that the 2 side surfaces can only travel a small distance. Or, to simulate a ice cube, the lock system is locked so that the 2 vertical side surfaces cannot be squeezed, and the stimulate sponge and the wet glass table similarly. The participants are asked to wear a HMD on the head and 2 tiny trackers on thumb and index respectively. In addition, An extra tracker was bonded with Muli to locate it in VR scenes. Then they were able to see the corresponding items rendered in VR and interact with Muli, which acts as a proxy to allow them to interact with four-weight vertical objects. Muli allowed users to squeeze and lift an ice cube and a coke bottle in VR. It also allowed users to squeeze a sponge and scratch a glass surface. We conducted the second study to evaluate the performance of Muli in generating witness illusions in the following scenarios: ice cube, coke bottle, sponge, and glass table surface. Specifically, we aim to answer these two research questions. First, could Muli stimulate witness illusions that people commonly experience in their daily lives? Second, could Muli stimulate different levels of witness illusions for each witness experience? During the study, participants were presented with this scenario in VR in a random order that were asked to rate how real they felt that they had touched the corresponding items on a Likert scale. For each test condition, we had Muli generate 3 levels of witness. To avoid any bias, participants were not allowed to see the Muli prototype. To answer our first research question, we plot out participants' ratings of their feelings of the corresponding items in VR. Results in chart show that the higher the temperature changed, the higher the participants' ratings of their feelings of touching the weight corresponding objects. To answer our second research question, we show the accuracy of recognizing correct witness levels for 6 test conditions. The results shows the participants were able to distinguish 3 levels of witness for ice cube, coke bottle, and sponge with 83% accurate or above in most cases when they lift or squeeze Muli. In contrast, the participants have lowest accuracy in distinguish the witness levels for the glass table condition. The result calls for more future work to investigate how to generate witness illusion when user only scratch a surface instead of lifting or squeezing it. What's more, the result also suggests that the lowest temperature level was the worst overall accuracy compared to other 2 temperature levels. One potential reason might be that when the temperature is too low, people would feel coldness more than witness. Our qualitative feedback also suggests that participants felt witness illusions during the study. For example, 10 participants tried to rub their fingers to draw them during the study, and all participants thought there was a witness generator. And 3 of them even constructed a mental model of the witness generator, which consists of a water sprayer or a water drop generator, a dryer, and a stiffness generator. It is worth noting that witness illusions disappeared once the stimulus were no longer applied to participants' fingertips. As some participants reported, it felt strange that their fingertips dry so fast, which was contradictory to their common knowledge about how long it usually takes for their wet fingers to dry naturally. And we choose not to ask users to lift the stimulated sponge because Muli was much heavier than a real pieces of sponge. Future work should be examine how to make Muli weight match the VR objects to enhance the immersiveness. To conclude, we have made 3 contributions in the work. We provide an understanding of the effect of temperature, pressure, and friction on the witness perception on fingertips with dry stimuli. Secondly, we present the design and the implementation of a prototype Muli that allow VR users to experience witness on their fingertips. Thirdly, we show that Muli can provide VR users with different types and levels of witness illusions when squeezing, lifting, or scratching it.
Thank you for watching our video presentation. And if you have any interests or questions, welcome to contact us.